We have a speaker well known to this club, Dave Bailey. Well known to give kind of physics-oriented presentations. Try to have some balance and have some a little more challenging and some not so challenging. Dave's are often a little on the challenging side. He says he's been an astronomer from before he was born because his parents were into astronomy, and he loves astronomy. I mean, he's addicted, right? I mean, totally. I don't know what kind of food you eat. If that hasn't been doing it. It can't be the snacks because I don't see him eating too much.
Alphabets.
Yeah, alphabets. Is there some kind of stars in cereal?
Hydrogen alphabets.
So, I always enjoy his presentations immensely. Tonight it's Planetkillers. Sounds ominous. In unstable orbits. That sounds even more ominous. Take it away, Dave.
Okay.
I will be your Ken Burton tonight.
Yeah. What I'd like to do is start out with the images. That way we know we have enough time to see the pictures.
All right.
Go ahead. Okay. This shows you where the Centaurs are. Centaurs are small planets. Well, some of them are too small to be called planets, even by me. And they typically are closer to the sun than the Kuiper belt. The green things here are the Kuiper belt objects. There's Neptune, Uranus, Saturn, and Jupiter, where they happened to be when this computer printout was made. And the orange things are the Centaurs. Centaurs have crazy orbits, like this one, for example. It's probably near its aphelion. At perihelion, it could be in here, around where Jupiter is. A lot of them have orbits like comets. In fact, they are comets. We'll talk about that more later. In here, this color here is the Trojan asteroids. And everybody knows that the Trojan asteroids are 60 degrees in front of Jupiter and 60 degrees behind Jupiter in their orbits. But they wander a lot. They are that distance from Jupiter on the average. That's why this is such a big blob here, and this is such a big blob there. Where's the Earth? The Earth is about where the rim of the sun is there in that picture. Next. Okay. This is the first of the Centaurs that was discovered. They didn't know it was a Centaur. They never heard of Centaurs. They thought Centaurs was some kind of mythological thing that was half man, half horse. And they found this asteroid. Was found, I think, by Walter Baade, and it was in 1920 or so. And you can see it's got an orbit, looks more like a short period comet orbit. Its orbit is bigger than Jupiter's orbit and smaller than Saturn's orbit. That does not mean that it goes around a circle between the two orbits. Because as you can see, it gets way closer to the sun than Jupiter. In fact, it gets almost as close as Mars. And it goes way beyond Saturn. This is typical. These numbers here just tell you where the thing was at the time that this printout was done. I have no idea what these yellow lines are. Next. Okay, I apologize for this fancy-dancy moving stuff. There will be cases where we would like to back up and look at some of the previous images.
Sure.
Because it'll bring in one, and then before you have a chance to see what it is, it'll bring in another one. This was done by Ken Burton. He knows how to make it work. I don't. You may be able to hit a key and stop the thing. I'm not sure.
No.
This is the most distant satellite of Saturn, which is commonly remembered by people, Phoebe. And it probably is a Centaur. Nobody's ever got a good image of a Centaur up close, a wild Centaur that's out there doing its own thing. But Phoebe orbits Saturn, and we sent spacecraft to Saturn, and they imaged all the moons that they could get at the time. So we have a fairly good image of what is probably a typical, although very large, Centaur object. I don't know what this is. For some reason, the texture of that crater looks different from the rest. Next. Okay, Asbolus. This is an unusually active Centaur. It changes its orbit about every 1,000 years on the average. No schedule. When does it do it? When it passes close by Jupiter and or Saturn. The gravity of Jupiter and or Saturn changes its orbit. And most Centaurs have strange orbits, but their orbits evolve rather slowly. Next. Same one, yeah. Okay, this shows you an idea of what Centaur orbits might be like. And it's a rather poorly laid out drawing. I would have laid it out different, but anyway. It shows you that some Centaurs are extremely inclined orbits. This is almost 90 degrees to the plane of the solar system. Here's where Jupiter's orbit is, Saturn's orbit, Uranus's orbit, Neptune's orbit.
Can I
Go
ask a
ahead.
question?
Yeah.
What's that green line, that green stuff along the bottom? I mean, I see the AUs, but,
Yeah. Oh, that's period in years.
oh,
Jupiter
okay.
has a period of 11 years. There's 10. The next mark is 11.
Yeah, okay.
Saturn is 29 and a half or something like that.
Okay, gotcha. I
Yeah.
got it. Thank you.
Go ahead.
Ready?
Okay, here's our friend Asbolus. Somebody plugged in the orbital elements of Asbolus into two computers and gave them slightly different input data. Tiny, tiny difference. And you see the black and the red. They only printed the red in this section because the black and the red were identical. Here's where the thing passed close to Jupiter and Saturn, essentially probably within a year or so. This is where we're at. Oh, centuries from 2000. Here's the year 2000. So this is 3000, 4000 AD, 5000 AD, 6000 AD, etc. They track each other exactly. The two computers just were
Oops, sorry.
turning out the same thing. Can you back up?
Yeah, he did.
Yep. Yeah, good. And here's another close approach to Jupiter. It did another glitch. And this is the size of the orbit in astronomical units. So the distance from the Earth to the Sun is that much on this scale. So you see this time the orbit changed by almost the size of the Earth's orbit, or the radius of the Earth's orbit. And then there's another glitch there, there's a glitch here. But then something strange happens. It's no longer predictable. The two computers now they're duplicating some of the glitches, and then something strange happens and they wander off like this. And 1,000 years after that happened, where is the thing? The distance from there to there is 10% of the size of the orbit. So it's wandered off into space, it's lost in computing space, somewhere in the solar system. And the difference that big in radius of the orbit means that the one calculation drifts around, all the way around the solar system relative to the other one fairly quickly. So the uncertainty in where it is now is more than 360 degrees with the sun at the center. So it's gone. Where is it? Who knows? The way to find out, of course, is keep tracking it with telescopes. Next. Oops. This is somebody's idea of a color diagram. It's not very useful in my opinion. But you can see that some of them are orangish, some of them are, I don't know, reddish, pinkish, some of them are almost gray. Next. Okay, here is a comet, 38P/Stefan Terma. I don't know if that's pronounced right. It's a Centaur. Well, I thought Centaurs were asteroids. Well, this one was a comet. And it passed fairly close to Uranus. They printed it out they told the computer to print it out at a time that would have these two stars be close together but not right on top of each other, so that there'd be room for the lettering. And you can see it's a typical Centaur orbit. It looks like a comet's orbit. The change in color is here is when the thing dives down to the far side of the solar system on the back side of the screen, or comes back upwards onto our side. And it doesn't tell you how much it's inclined, but you can see the line of nodes is from there to there. And it goes in as far as Mars, and it goes out beyond Uranus, so it's a pretty eccentric orbit. Next. Okay.
Hey Dave,
Yeah.
do we know of any centaurs that exhibit a comet-like tail by any chance, or is that?
Yes.
Oh, they do, okay.
In fact, if you look at the front page of your handout, it says something like Centaur objects, short-period comets, and distant satellites. All three of those are the same thing.
Same thing, okay.
Like a distant satellite like Phoebe, comets, asteroids, they're all the same. And what seems to distinguish them is chaotic orbits. Their orbits keep changing. Sometimes they drift a little bit. You remember the picture of the Asbolus, the graphs? Sometimes they go on like this, and then we go glitch, and then go glitch again, and yeah, go.
Oh, sorry.
Away. Yeah, this section here, it's drifting, and then suddenly it goes a glitch. Well, past close to one of the major planets then. And this one likewise, it's drifting. There's perturbations due to planets, but it never gets really close to a major planet. And then suddenly it does go close to a major planet, it goes glitch. And then, so, next. Well, you have to go several now. Yeah, okay. Someone did some computer projections to see how long a particular object would have essentially the same orbit, the half-life of the, I'm not quite sure why they picked that name. The half-life forward, meaning starting in 2000 AD and going forwards to 3000, 4000, 5000. And these 7 objects that they have times for have half-lives between 860,000 years to 11.1 million years. You can see that most of these, they're not totally crazy in what their orbits do. They drift slowly. Asbolus was a particularly unusual example because it did a glitch in the year 4713 or some such. And then after that time, who knows where it is? The computers don't know. These particular ones change relatively slowly. Between 1 and 10 million years, essentially. But that's really fast for orbital change in the solar system. Next.
Dave, when you talk about half-lives, you mean the change in orbit, or?
I don't know what made them use that term. There's nothing about radioactivity here.
Yeah. I don't get it.
Yeah, I don't get it either.
But that has to do with the orbital stability.
It may be that what they have in mind is, if you're looking at a particular atom that has a radioactive nucleus, you don't know when it's going to decay.
Okay.
You know it will eventually because it's radioactive, but you don't know when.
Right.
And in this case, maybe that's something that they have in mind because these things, they drift a while, and sometimes they don't drift at all, and then suddenly it goes right past Jupiter, and bing, now it's in a totally different orbit because of the slingshot effect. What have we got here? Miriam, moon of Neptune. Yeah. This is probably the most massive of all the of all of them. Centaurs, well, most of them are less massive than this. There's a printout at the back page of your handout that shows the sizes of all the distant satellites of the major planets, Jupiter, Saturn, Uranus, and Neptune. And that's the best source I know for the size distribution of Centaurs. Because we got lots of data on them, and we've got spacecraft flying past a lot of them. Whereas if you look for the wild Centaurs that are out in the middle of nowhere, you have to slew your telescope a whole lot. You have to do a lot of calculation to know where to point it. Whereas if you're just looking at Jupiter, you can see dozens and dozens of Centaurs rather quickly. So there's another example of what a Centaur probably looks like up close. Nobody has ever got a good picture of a wild Centaur. Next. Oh, Nereid also, by the way, it probably weighs as much as all the other Centaurs combined. And that's also true for Phoebe, the distant moon of Saturn. It probably weighs as much as all of the smaller Centaurs combined. That's true for the first few, maybe the first 10 items on the list that's on your last page. Okay, outer moons of Jupiter. This is sort of interesting. I wish they'd use smaller type, but some of those can't be read. And Jupiter is in there somewhere. It's probably right about there.
Great, yeah. Oh dear, what, I don't know what happened there.
Oh, well, apparently it's not just the orbits that are unstable. It's also the graphics.
Jupiter is the blue line, right?
The blue line? Yeah, that's probably the orbit of Jupiter. So probably Jupiter is somewhere along that blue line. It's probably right about there. You should have a dot there, but they didn't. The outer satellites of the major planets, basically some of them orbit direct. So they go around, look at it from the north, they go around this way. And some of them orbit in retrograde. Most of them are retrograde. The retrograde ones have larger orbits. And there is reasons why that's true. And if we have time, we might talk a little bit about it, but it's low priority. Anybody who wants to know about that can talk to me later, either at the Coney or at the next club meeting. Next. That image, by the way, was in there partly because you had an idea that, yeah, you can observe an awful lot of Centaurs quickly if you concentrate on the moons of the satellites rather than the wild Centaurs. There's a Comet Shoemaker leaving 9, which is, guess what? A Centaur. Well, it was a comet initially, then it passed close to Jupiter, and it became a moon, because it was then in orbit around Jupiter. Then passed rather close to Jupiter, and the gravity from Jupiter split it up, and the pieces are now scattered along the orbit. It's probably going like this, in this direction. And then, so first it was a comet, and then it was a moon. Of course, all along it was a Centaur. Then the pieces hit Jupiter, and what did they become? Part of Jupiter. Next. Oh, okay. Hey, you're able to
There you
control
go.
this thing.
Sort of.
Yeah, wow. How do you do this? Anyway, these blobs here are the various puffs of smoke or whatever produced by those various objects. I think there's another one here.
Yep.
For scale, this is about the size of the Earth. So these are large, large clouds, if that's what they should be called. Next. Okay, an ultraviolet view of the same thing. That's the shadow of a satellite, I presume. Probably Ganymede or Callisto. Probably Ganymede. I'm guessing Ganymede because it's relatively large. Of course, the shadow could be larger than the moon.
Right.
And here's various. I don't know what those. Oh, these are the letters that refer to the pieces of the comet. Next. Oh, that showed the last turn. Oh.
Ken, what happened?
Goodness gracious.
He's losing control. I thought he had control of this. You were doing very
Ken's
well
fault.
before.
Ken's fault.
For front door spring,
I think this is
2015 maintenance. I
Oh,
don't know.
oops.
There's John Kennedy.
Yeah.
Oh dear.
It's a secret code.
The truth is out.
An unexpected sighting of John Kennedy. Okay, is that it? That's probably it.
Something like it.
I don't think it's worth trying to capture the others. So, good. I'll look quickly and see if there's anything that I specifically want to talk about that couldn't really get onto the screen. A picture of a comet that has a circular orbit. 29P, Schwarzmann-Bachman.
Here we go.
Here we go.
Oh, okay, that's the final orbit. Yeah, here's where presumably it broke apart in pieces. Nobody was watching at the time, but that's most likely the time that it occurred. Okay. And the next one, oh, there's Schwarzmann-Bachman. This comet is unusual. It was discovered, I believe, in 1927 or sometime like that. And here is the orbit of the thing. And it looks like Jupiter's orbit, except it's about one astronomical unit beyond Jupiter. Don't comets have long eccentric orbits?
Usually.
This one is round.
Oh,
It was at the time, maybe still is, the only comet which has been observed to produce outbursts, the cometary outbursts, all the way around its orbit. In a typical orbit, it bursts out about 100 times. So somehow or other, it manages to be very active without ever getting close to the sun. And I don't know why that is. I presume the activity is more like a geyser than a volcanic eruption, because it never gets hot.
Is there anything left of it?
I believe it's still out there.
Eventually it would dissipate.
And so, at one point, there were 3 objects that had been discovered out there, and the third one was Chiron. The second one was Schwarzmann-Bachman 1, number 29P. P means periodic comet, and I guess that's the 29th periodic comet that was adequately caught so that its orbit was well known. And then the first one was Hidalgo, the asteroid in a comet orbit. Second one was a comet in an asteroid orbit. The third one was Chiron, which was identified as an asteroid, and then like 11 years later, it turned into a comet. And at that point, with 3 of those weird objects out there, people started to take notice. What's going on? Why are the distant asteroids so weird? And then sometime after that, somebody, who I think was a committee of the IAU, small body nomenclature, I think, they decided to make it official and call all these strange objects by the same name, and they decided to call them all Centaurs. And at least at first, they tried to name all of them after mythological male centaurs. I don't know if there's any known female centaurs in mythology. So, but I was a little bit surprised that there were quite a few male centaurs that actually had names, known names. Of course, our expert Diane could probably explain this way better than I can. Yes? Oh, you're just stretching, you're stretching, okay, sorry.
Did they soon run out of names?
I presume that they
Yes.
did.
Then they moved down to Centaur wives.
Really?
Chariclo,
There are centaurs' wives?
that's Chiron's wife.
Okay.
What was it again?
Chariclo, it's a centaur
Chariclo?
with the rings. It's the largest one that we know where it is.
Oh, there you go.
Oh, interesting. Some centaurs have satellites orbiting them.
Hylanome is is a female.
It's female, okay, okay.
So
Oh,
Dave,
the first, yeah,
I'm getting a little confused. By definition, is a comet because of composition or
No.
because of orbit?
neither one.
Neither one.
It's the outbursts.
The outburst.
It goes poof.
That's a
It
comet
develops
because
a-
of the outburst.
It develops a temporary coma, which is it's an atmosphere.
Right.
Coma of a comet is an atmosphere. Way bigger than the Earth's atmosphere, by the way, but anyway, yeah.
So what does that mean, like it's composed of?
Nobody knows.
Well.
Nobody has yet brought back a piece of a comet.
No. Kind of what I'm asking is, don't certain elements have emission or adsorption?
Yes, you can do spectroscopy on the light from it. What did you say, Diane?
I was saying the conventional wisdom used to be that asteroids are made of stone or metal or
Right.
something in between, and
Well, that's
comets
what I
are
was
are
kind of-
snowballs, you know,
Yeah.
the dirty snowball. And the more research we do on comets and asteroids, the more we learn that that's a pretty arbitrary distinction.
They,
Yeah,
I
one
claim
good
that,
example. Good
I claim
example
all
is,
asteroids started out as
Yeah.
comets, and they just dried out eventually, and there was no water left, and now you call them asteroids.
Yep.
Yeah?
Yeah, I was gonna say, what do you call a comet that's gone around enough times that it's pulling all its volatiles off? It's an asteroid. They're like that now.
And when it's an unstable orbit, you call it a Centaur. No, the first several pages
Is
of your
there a-
handout are kind of,
I knew David.
I didn't intend to cover them, actually. I've covered a good bit of things in there just because we had the pictures to look at. I tell about how asteroids are easy to defend against relative comets. Comets are difficult. The toughest impactors are comets. They can hit us without any near miss warnings. Asteroids, they pass close to the Earth several times before they hit us. They can sneak up on us stealthily, the comets. They can sneak up on us stealthily by approaching out of the sun's glare. They may, on the average, be larger than the near-Earth asteroids. For example, the largest Kuiper Belt object is way larger than Ceres, the, quote, largest asteroid. It's also larger than Pluto. And mass for mass, comets are many times more destructive than asteroids because of their faster approach velocities. Since their kinetic energy is Ke equals 1/2 mv squared, a comet approaching at 10 times the velocity of an asteroid will strike with 100 times the energy, pound for pound. In the old days, when many folks thought comets were made of fluffy material, some of them would say that therefore we needn't worry about comets impacting the Earth. That was a silly idea even then. Ke equals 1/2 mv squared. Remember, there isn't a separate formula for fluffy material.
Dale, are you gonna let these equations go unchallenged?
What equations? What? Oh, yeah, you promised to get me an image of a mythological centaur.
There you
There
go.
it is.
Dave,
Yeah.
can I back up to the discussion of asteroids and comets?
Yeah.
I either read or heard somewhere that typically comets come from outside the solar system, the Oort cloud, effectively.
No, they don't come from the Oort cloud.
No,
They come from the Kuiper Belt.
okay.
There'll be a diagram showing you what the flow of the Centaurs is. The Centaurs start out in the Kuiper Belt.
Okay.
And then a lot of them get kicked out into the Oort cloud by slingshots from Jupiter. The problem with getting comets from the Oort cloud is that the solar system is a teeny tiny dot. Not just the sun is a dot, the whole solar system is a dot from a typical location of the Oort cloud. If you want to drop a comet from the Oort cloud into the sun, you have to stop it dead in its tracks, and by dead I mean dead, dead, dead. Then it can fall straight towards the sun. Short of that, the Oort cloud comets are out there and they're not coming back. By chance, some of them do. And we do observe high velocity comets sometimes where the best velocity vector that the computers can produce does seem to have zero, cross momentum. You say, well, yeah, maybe it did come from the Oort cloud. But you can't get a large number of them that way. It's
Okay.
just too unlikely.
Conversely, asteroids can travel from the Kuiper Belt into the solar system?
Yeah, yeah,
Okay.
yeah. I claim all the asteroids came from the Kuiper belt. All of the comets came from the Kuiper belt, except for very few came from the Oort cloud. Anyway, what are the things you got for us?
That was it.
That's
That
it?
was-
Okay, cool. Yeah, I talk about chaos here. And we talked about 8405 Asbolus, which is the one that has the glitches every 1,000, not every 1,000 years, because that's unpredictable too. Whenever it passes close to Jupiter, its orbit glitches. Another rather scary case is Centaur 1995 SM55. Sometime in the 20 years since 1995, it has actually gone missing, lost in space. It is one of the largest Centaurs known, perhaps the largest of all. It may weigh somewhere around 20,000 times as much as the impactor that killed off the dinosaurs. A real planet killer, for sure. And nobody knows where it is or where it's going. Okay, Walter Goddard, yes. Comet Schwarzmann Bachman. I have to rehearse pronouncing that because I don't
It's
speak very
good.
much German.
Schwarzmann Bachman.
Schwarzmann Bachman, yeah. I think they collaborated just so people have trouble pronouncing that.
Just to make trouble.
Yeah. Okay, yeah, the IAU's Committee on Small Body Nomenclature decided to make them all Centaurs. JPL knows of 291 Centaurs, and there are 61 more objects in Centaur-like orbits out of the Uranus-Neptune region for a total of 352. I would count all 352 as being Centaurs with possibly a few exceptions. Those might be the circular orbit ones. Because circular orbit, how can it be chaotic? If it's orbiting distant from any planet's orbit, its orbit should be totally stable. So do you call that thing a Centaur, since Centaur orbits are supposed to be chaotic? Interesting question. One estimate, most astronomers agree that the great majority of Centaurs have not yet been discovered, especially the small ones. One estimate says the count of objects with diameters in excess of 1 kilometer ought to be 44,000, more than 99% of them undiscovered. This 44,000 is a tiny number when compared with a huge swarm of main belt asteroids. That's your cue, Bob. How many main belt asteroids do we got?
667,000 last time I looked, but hold on.
Well, that's only 15 times as many as these.
Well, 678, 789.
Okay, so that's 15 times more main belt asteroids than Centaurs. Some of them might be counted twice, because some of the Centaurs might be called main belt asteroids. Anyway, this 44,000 is an even tinier number when you look at the volume of space in the main belt of the asteroids and the volume of space out in the Centaur region. It says here, I just calculated the approximate volume ratio, and I got 193 to 1. There's a whole lot of space out there in the range of Uranus and Neptune. So they're spread out pretty thin out there. Orbital diversity, yeah, I talk about that. How the orbits can be different. They can be highly inclined, they can be very eccentric, they can be only as eccentric as the Earth's orbit. They can be right in the plane of the solar system. They're just sort of randomly oriented. About 1 in 30 revolves retrograde around the sun. And my comment is, any theory about the origin of Centaurs had better be able to explain why 1 in 30 of them go around the wrong way. I would also invite somebody to tell me about this asteroid, how it gets its name.
Asteroid spelled backward.
It's a retrograde asteroid, and somebody had an idea that that'd be a good name.
Alright, so that sounds painful.
What was that? That was less than 10 seconds. I think it was more than 5 and less than 10. So, good job.
Well, I'm a big Swallow rotative.
Okay, where are we at? Early history, yeah, we already did that. Yeah.
Are you gonna go into the definition of planet killer?
Yeah, planet killer. Planet killer is something that, if it hit the Earth, would kill off all life, not just the dinosaurs. Yeah. And how does it do that? Well, mostly by heat. There are microorganisms that can withstand severe shock. There's live bacteria have been found in the water systems of nuclear reactors. And down in the ocean trenches, on the trenches, in the rifts, ocean rifts, organisms routinely manage to survive in water that's considerably hotter than the boiling point of water that we are used to here on the surface of the Earth. They can live in water well above 212 degrees. But I believe that there is some temperature, probably around 500 Kelvin, which is the temperature of a hot oven, but not on its cleaning cycle. 500 Kelvin is going to be, you're going to find that even the most heat-resistant proteins start to denature. And I claim when that happens, the organism dies. And if you can raise the temperature of the entire biosphere of the Earth to temperatures around 500 Kelvin, then I claim, everything dies. How do you do that? Well, one source of the heat is the impact itself. But the other one may be more important, which is exposing a huge amount of magma. You've got a crater 1,000 miles wide. That's a long lot of exposed magma, and it ought to heat up the entire atmosphere and maybe the oceans to high temperatures. It's interesting to notice that the deep oceans will not boil. They'll get hot, but they won't boil because under those pressures, water cannot boil.
Mm-hmm.
It turns into vapor continuously without a surface and without bubbles. But anyway, so that could be how a planet killer could work. How big would a planet killer be? Well, I'm told that the object that killed off the dinosaurs probably was about 4 kilometers radius, the other way around, 10 kilometers diameter, something like that, right? Does somebody remember what's the latest on the size of that object? I think it's like 10 kilometers diameter.
It's right around there.
Yeah. And I think an object 10 times bigger, no, 10 times bigger, twice the size. Instead of 10 kilometers diameter, make it 20 kilometers diameter. That's 8 times the mass, assuming the same density. 8 times the hit, I think, would have killed off more than just dinosaurs. So I'm thinking somewhere around there might be the smallest planet killers. When do we end? How much time we got?
9:30.
9:30. Wow. Okay, well, let's talk.
So it wouldn't have to blow away the atmosphere entirely or something like that, would it?
How long would it last?
It's hard to blow away the atmosphere entirely. Even if you blew away all the nitrogen and oxygen, you still got an atmosphere. What it's made out of? Steam.
Yep.
And in fact, atmospheres in general are hard to get rid of if you have a planet like the Earth, a massive planet like the Earth. People talk about, well, how could water escape from the top of the atmosphere? And my comment is, what do you mean water? Water boils at 212 degrees. How about nitrogen? Nitrogen boils at 77 degrees Kelvin. It's way more volatile than water. We should have lost all our nitrogen eons ago. What keeps it in? Nothing, except gravity. It's a gas. It should disperse into space, shouldn't it? No. Gravity. Yeah.
Suppose such a planet killer hit Earth and sterilized the planet.
Yep.
What about stuff ejected
Yeah.
from the impact,
Yeah.
which would be loaded with life?
Yeah. Could land on Mars.
Yeah, or
Maybe that's where we got our
Or
life, was
going
from
to-
Mars.
go into low Earth orbit
Yeah.
and decay back in slowly.
I think you've been reading page 6 or so.
No?
That's discussed in here. Okay. Yeah, if the Earth is completely sterilized, life would start again on the Earth within years or decades, as soon as the surface got cool enough, because there's satellites in low Earth orbit. One of them crashes down, presto, new life, because of the contamination, bacteria on the satellites. They're supposed to be all, sterilized, but I'm sure not all of them are, totally. Did you have your hand up? No? Okay.
Yeah, I got my hand up.
Yes?
There's a website, I don't know, most people might know it already. It's NEO, Near Earth Orbit, Near Earth Object.
Near Earth asteroids, it's
Yeah,
NEA.
It has
Object is
animation of all the known objects. You can select it.
It's right there on your computer, isn't it?
It can be.
But, okay, I just think that's a very neat
Yeah.
program they have.
I have a little comment about types of orbital changes. With a typo, it has of orbital changes written as one word.
Yeah, I noticed something went wrong with
Something
the
went wrong with that
spacing.
page. Yeah.
I think the spacing maybe in your printer, or
Yeah,
I don't know.
no, it's not the printer. No, it's not the printer. No. Anyway, I'm not sure which page this is. The page that has the diagram in the lower left corner, I'll discuss. Because somebody was asking about things moving around in the solar system. And I have a little diagram that shows my idea of where the Centaurs come from, and you can see there's places shown there in the diagram. One of them is Kuiper Belt and Centaur region, and then another place is Oort cloud and interstellar space. There's Jupiter slingshot, which is the thing that can happen to a Centaur when it gets close to Jupiter. Impact on Earth, inner solar system, comet burnout, and impact on the sun. And the little arrows connecting the different places and events have numbers alongside of them, and that gives my guess is the relative numbers of Centaurs that go along those arrows and change their status. So you can see that my estimate is that for every 18 Centaurs that move from the Centaur region into Jupiter, close enough to do a swing by Jupiter, for every 18, 5 of them, it looks like they get returned to the Centaur region. 5 of them are ejected out into the Oort cloud and possibly out of the solar system entirely into interstellar space. 2 of them hit the sun. 6 of them do a comet burnout thing in the space in between system, and 6 disappeared somehow. Yeah, if a comet approaches the sun fairly closely but doesn't actually hit the sun, then it will burn out fairly quickly because it'll lose all its water and it'll end up as a meteor shower. And the arrow pointing to the left says impact on Earth, and the number on that arrow is 0.0002. Why such a tiny amount of flux of Centaurs hitting the Earth? Well, it's because the Earth is a very, very, very tiny target. then you start doing more calculations. You say, okay, if that Markov diagram is correct approximately, and you can play around with it, change the numbers if you like, and have your own estimate of where most of the Centaurs end up going after they can pass by Jupiter. Do some more calculations, and you discover that, what's a time scale? I know on the right-hand side. What's a time scale of the Markov diagram? Or equivalently, how many Centaurs flow through the diagram per million years? And I do some math based on the computer stuff back on page 3. And I get 2.02 million years. So typically, a typical Centaur orbit changes significantly in 2.02 million years. And they vary a lot because, as you saw, some of them were changing in 1 million years, some faster than that, some in 11.1 million years. And you can then calculate things, and you know that there is also an estimate from page 4, I think, yeah, that there are 44,000 asteroids out there that are Centaurs. And of course, that number was just pulled out of the air by somebody who doubtless had thought about it for weeks on end, but it's still a guesstimate. And from those two, you can calculate like about every 46 years, on the average, something interesting happens to a Centaur somewhere in the solar system. Well, that's interesting. Every 46 years, either there's a Jupiter slingshot that takes place, or a Centaur falls into the sun, or it gets launched out into the Oort cloud. That's an interesting number to know. But most of those interesting events are not so dramatic. We saw the Centaur 8405 Asbolus change its orbit by about half an astronomical unit every 1,000 years or so, but we never saw it collide with anything. And those frequent things that happened to Asbolus 4602, whatever it was, 8405, yeah. All kinds of things were happening to it every 1,000 years. What's going on? It should be every million years, shouldn't it? But we just calculated the half-life of an orbit of Centaurs on the order of 2 million years. So that tells you that some Centaurs are frequent flyers. They're much more active than, how long ago did Bill land on an airplane? Decades. I'm not a frequent flyer, but some of them are.
What part of the orbit makes certain ones more likely to be?
They just have to pass near the orbits of Jupiter, Saturn, Uranus, and Neptune. And just crossing over doesn't tell you anything. Like, here's the Sun, here's Jupiter's orbit, here's Saturn's orbit, here's Uranus's orbit, and here's Neptune's orbit, you know, like that. And you have a Centaur that has an orbit like this. You say, oh my God. That can interact strongly with the Sun, Jupiter, Saturn, and Uranus. Well, no, maybe not. If that whole orbit is tilted like that, then the only thing it interacts with is the Sun. Because as it's coming out this way, it goes way above Jupiter, way above Saturn, Uranus, and Neptune. Coming back in, it goes way below Neptune, Uranus, Saturn, and Jupiter. So you got to think in 3 dimensions. Find what the tilt of the orbit really is.
I'm sorry, but don't you have to think in 4 dimensions? I mean,
Well,
right?
yes, because let's suppose these are all in the same plane. Then it comes right past Saturn here. But when the Centaur is there, Saturn is here. And then passes right through Jupiter's orbit, say. But at the time, Jupiter is there. So yeah, you do have to think in 4 dimensions.
Cool.
However, if it goes around for 50,000 years or so, it's going to pass those intersection points when the planet really is there, and then it will get a gravitational slingshot and it'll go somewhere else. Its orbit will change dramatically when that happens.
So, somewhat of a guiding factor is the inclination of the orbit once they're closer to the solar disk have a higher percentageal chance of
Yeah.
being affected.
And paradoxically, if it's orbiting in the direct direction, it's gonna respond more to a close approach than if it's going retrograde. Because if it's going retrograde, it might go right past Jupiter, but Jupiter just goes whoosh past and doesn't affect it as much as if it was catching up to Jupiter slowly. You get more delta V in kilometers per second.
The only mechanism for a retrograde asteroid or Centaur, or whatever you wanna call them, one that's been inclined so far that it's gone over to the dark side? I mean,
Yeah, my guess is that it's not a gradual process. I think it just passes real close to Jupiter, or goes inside of Saturn's rings or something, and then it can go retrograde, yeah.
so you think it just turns right around?
An object that goes past Jupiter can get slung out into interstellar space. It can also be dropped into the sun. There's enough delta V available from Jupiter's gravity. And if it can drop into the sun, it can certainly drop a little bit reverse into the sun, and then it's in a retrograde orbit.
Yeah, but I mean, like, so how do we find these guys, or gals, or whatever they are?
Good question. And in fact, it's in the same category as comets. Comets can sneak up on us. And once a comet is a...
That's,
No, yep.
no,
Yeah,
that's
that's
just,
good. That's good.
or can, oh,
That's good. What time you got?
9, 10?
I mean, when
Quarter after
are we
9
supposed to,
approximately.
when am I
13
supposed to run
I
out of
think
time?
5 to 10 minutes would be good.
Okay, that's cool. Okay, I lost your
Yes.
question. Yeah, what were you
No, the
saying?
question was, how do we find these guys?
Oh, how,
Girls or
yeah,
whatever
gotcha,
they are?
gotcha. Yeah. Once a comet is observed,
Mhm,
then we have got a good orbit on it.
mhm,
But it can sneak up on us by coming out of the sun.
mhm. Wait a
And,
second.
and
No,
if they're,
Wait, I got a question.
yeah, go
I
ahead.
thought I read somewhere that there was a plan or something for, gee, I don't know how to say it, sort of, but a simultaneous geolunar synchronous orbit that just kind of goes around both of them for a observing thing? I don't know what I'm talking about.
Yeah, there are orbits that you can put an object into, a spacecraft. One that's very attractive is the Earth L4 and the Earth L5 points. And the way that works is, here we go, mine will stay black. Here's the Earth's orbit going around the sun. Here's where the Earth is. Here's the sun. Then Earth L5, I think, is here. Earth L4 is here. And the spacecraft in those locations will sort of stay there for a long time without you having to use a lot of
Oh,
rocket
gotcha.
fuel.
Yeah, yeah.
And the nice thing about those is, if there's a comet that's sneaking up on us, and it just came around the sun like this, and now it's coming like this, it's coming at us out of the sun.
There you
Well,
go, yeah.
these two have had a good shot at seeing it all along.
Right, right, right.
And it doesn't give you years, it doesn't give you decades warning. In the case of an asteroid that's gonna hit us, you got decades of warning, because it'll come really close to the Earth, and then it goes around a few times, and it goes around a few times, and goes
Yeah,
around.
yeah, it
And then
spirals
decades
and
later, it
all.
actually hits the Earth. So you got lots of warning. In the case of a comet, you've only got a few years to a few months to a few weeks, or no warning at all. These satellites at L4 and L5 will see the thing coming, so that maybe you've got a year warning instead of a week.
Yeah, yeah. Cool, well, whatever. I mean, that's cool, but-
So,
Yeah,
so obviously we should worry about asteroids least, but should we worry more about Trojans or more about conventional, or Centaurs, or I was thinking
well,
those are
the thing
Trojans.
think about a normal comet is, once you've observed it and you've got a good orbit for it, then you know it's gonna stay in that orbit, except maybe not. Because comets, when they're close to the sun, have rocket propulsion
Mhm.
from their geysers that spew massive stuff out into space. But it's not as bad as a Centaur. Because a Centaur, you know in advance, has a chaotic orbit. You know that it goes close to one or more giant planets on occasion. And so, if it's a really bad case, let's say it passes close by Uranus, Saturn, and Jupiter.
Mm-hmm.
A pass by Uranus can alter the pass by Saturn. The pass by Saturn can make it go past Jupiter when it otherwise wouldn't have done it.
And we lost one of the largest,
One of the largest ones, possibly the largest.
possibly the largest.
It wasn't
one.
observed long enough for us to know how big it really is, apparently. The confirmation, it may not even exist, because the observation maybe didn't get confirmed. I don't know the history of it.
So it could be out in interstellar space, or it could be.
Yeah, there's ways of, if you don't observe at the right time and looking in the right direction, you can be looking at something that you didn't think you were looking at. When Pluto was being searched for, all the observations that were made that were not looking directly away from the sun had to be like thrown out, because there were too many ordinary main belt asteroids that were caught by those pictures that were near the stationary point where they're going from retrograde apparent motion to direct and vice versa.
Right.
And so they're moving really slowly, and they look like something that's 30 astronomical units away. And oh, there's Pluto. Oh no, it isn't Pluto. It's just a normal asteroid. Hasn't been discovered yet, so you get credit for discovering it, but it's not Pluto. So, but if you look straight away from the sun, then anything that's moving very, very slow cannot possibly be a main belt asteroid.
So there's many asteroids named Pluto.
Yeah,
There
maybe.
you go.
I think I'm, yeah. I'm gonna officially say that I'm done, so now I'm just asking her questions.
It's not a question, actually. Just the other day, I got something sent to me, and NASA is now actively asking amateurs to help them find asteroids. And with the way to do it, it's called the Asteroid Data Hunter, which is a app, which if Ken Burton was here, we could tell you.
Yeah, yeah.
Okay.
And if
It's
Gary
an app
Ross
that
were here.
Yeah, and it downloads to a Windows-type machine or a Linux machine, or to a, I think Macintosh too, I think, yeah. I think, not Macintosh, I mean, yeah, I think it's, yeah, it does go to Mac, it goes to Mac too. But what you do is you take a picture of any amateur telescope, and you put in this program that automatically matches up against all the known asteroids and finds them. It's pretty much a idiot-proof, just, push your dummy type to run it. And, so if people are interested at all taking pictures through telescopes, or certain people I know personally.
You can go and discover asteroids.
Yeah, might discover an asteroid.
Yeah, yeah. I found something interesting here on the last page, where it shows the size distribution of the distant satellites. The most distant, as far as I know, the most distant satellite of anything in the solar system is NESO, anyway, NESO, which orbits Neptune with a semi-major axis of 48 million kilometers, or 1/3 of an astronomical unit. That's distant. Like if there were an object orbiting Venus at that distance, it could crash into the Earth just in its normal orbit around Venus. It also has the slowest orbital period, 9,374 days, which is 25.7 years. This is a moon that goes around in 25 years. Sort of interesting. Rather weakly bound to Neptune, I would say. Probably every revolution, this is true for a lot of these distant satellites, every revolution of the satellite is different from the previous one, because they're so far out, and the gravity of other planets and the sun changes their orbit every time around. Yeah.
I assume that they were called Centaurs because they're an amalgamation of comets and asteroids.
I think so.
which all those being the same, should we just start calling everything Centaurs or
Oh yeah,
Griffins?
the moon is
or-
a centaur, right?
I mean,
No, the moon is too close to the Earth.
is it time to reformulate our definition of certain objects?
Maybe. Normally, I am strongly opposed to orbital definitions. I like objective definitions. Objective, I mean, it relates to the object, not to the orbit that it's in. And my favorite example is, you go to the Indianapolis, the Indy, and you got a track. It's called the Indy track. And you've got cars going around it. They're called Indy cars. If you drive an Indy car off the track and go and park it in the bus station, does it magically turn into a bus? No, it's still an Indy car whether it's going around the track or not. So that's an objective definition. It relates to the object and not to the orbit. In the case of Centaurs, I very reluctantly favor an orbital definition because the essence of a Centaur is that its orbit varies chaotically.
How long has the term been used?
Centaur?
Yeah,
I
for
don't
these objects?
Well, let's see, it's at least, when was?
1970s? When the
Yeah.
third one, it was 1975? When
75,
third?
77,
77?
something like that. So, yeah, that's probably when the word started to get used. Yeah.
So, if you look at the moons of Jupiter or Saturn, some of them orbit close to the planet. They're deeply bound to the planet.
Yep.
Others are way
Those
out
are not
there.
Centaurs.
Yeah, yeah. So,
Those are real moons.
so there must be some way of differentiating the two categories of moons.
I use an arbitrary number, 100 days. If it orbits the primary in less than 100 days, then it's not a Centaur. Iapetus orbiting Saturn in 79 days.
Good,
Not
give
a,
us the camera.
not a Centaur. But there's an object orbiting Jupiter in 130 days, which I say is a captured Centaur. And that gap between 79 and 130, the easily remembered number, 100 days in the middle of it, that's what I use as my, my difference.
Okay, so 100 days is a nice round number.
Yeah.
But physically, there isn't that much difference if you would define the difference as 110 days or 90 days being the differentiator.
I wouldn't move any objects into the other category because there's this big gap actually between 79 and 130.
Well, are you saying that gap exists for moons around the other main
Yes.
planets?
Yes.
Why?
I don't know. It's a lucky circumstance for me because I could pick 100 days and say anything slower than that is probably a captured Centaur.
Well, that would suggest if that same gap exists around the other gas giants,
It does.
then there's some physics there.
It may be. Maybe.
It's not total, it may appear to be arbitrary, but it may not be.
Well, how many do we know that are above 100 days? Is it?
It's a list on the,
Okay,
that list there. That's a few.
okay.
This starts out with the largest objects. Near it is 170 kilometers in diameter, I think. And then it goes down to a half of a kilometer, no, it's radius. Half of a kilometer in radius is the smallest thing listed here.
So Dave,
All right.
based on your talk,
All right, last question.
is it reasonable to think of Pluto as a centaur?
Possibly. It's certainly in the Kuiper belt.
So we're gonna get a picture of it in a few months.
That's true. When we do, it'll be the best picture yet of, well, no, not the best picture yet, because all those captured moons, we got really good pictures of that, way better than Pluto. If I'm correct, that those are all captured Centaurs.
All right.
Good job.
After After our meetings at Macomb, we continue the discussion, if you'd like, at the National Coney Island on Van Dyke, just north of 12 Mile. So it's about a quarter mile north of 12 Mile, on the right. So on the east side of Van Dyke. All right, have a good night, and hopefully we'll see you at Cranbrook.